of CS101 for the spring semester. Um, I'm your host, Scott Manley. Not really. Um, if anybody knows who Scott Manley is, let's get a thumbs up or an emote in the chat uh, for Scott Manley. Woo, Scott Manley. Um, all right, so two things wanted to do today. The first was to talk more about some of the circuit kind of stuff for funsies to how processors actually do their thing. And then the second was to do any Q&A over the assembly stuff that's sort of more general in nature. If you have um, specific questions where I'd have to look at your code, then obviously we'll have to do that kind of one-on-one. But for more general questions, I'm happy to take those. So let's start with general questions over the assembly business. Just type it in the chat, hop in the Discord so I can hear you. One of the two. Let's see how many hundreds of thousands of people we have here. 0 people watching. Wow. Looks like we got 6 of you in the Discord chat, but 0 people watching. I'm offended, guys. So, oh, 7. Okay, there it goes. The counter just hadn't updated. Yeah. So we got any general questions over the assembly? So, determined to finish this project, says Mr. Sarajewski. Yeah. Well, good. Um, it should be fun. Teague's finished it. Um, he got obsessed and finished it last weekend. Um, so, yeah, once you get kind of over the hump of assembly code, then it's kind of like, oh, this isn't so bad. I'm a wizard now. You're a wizard, Harry. So Tyler, how you doing? Patrick, we're making progress on the project, hopefully. Assembly, it's hopefully starting to make some sense. Yeah, so. Okay, well, assembly is picky, right? It's super picky and super technical, and being off by one letter in the emulator will totally break everything. So you have to be really careful um, and take it slow and document your code. So write notes to yourself and maybe use scratch paper and whatnot to kind of plan things out. It's not too bad once you kind of get to it. All right, but any general questions over the assembly stuff that I can hopefully clear up, and if not, we'll talk some more circuity stuff for funsies. I need to get like sound effects so I could have like the cricket noise, and I can hear you. Statements. Okay. Yeah, good question. So let's look back at our cookbook to our if then and our if then else kind of thing. So let's actually do the if then else kind of thing. Um, so um, basically, what's funny about the um, if then else is that you actually, in assembly, or at least for this processor, you actually put the else case, well, you can put the else case first. Okay, so there's a couple ways to do it. This is one way that we wrote it, which was so here was our sort of idea that if the condition is true, whatever the condition is, then you do thing, and otherwise you do other thing. Okay, and maybe you do some stuff before you get to the if conditional, and maybe you do some stuff afterwards that doesn't matter whether or not you did the if versus the else case, you're always going to do the more stuff. Okay, so the meat of it is really this chunk here. Okay, um, which is you've got to compute whatever the condition is. Okay, and for the purposes of the programs that you guys are writing, those are going to be things like is the number odd or even, or is the number negative or not? Um, those sorts of things are what I mean by a condition. So, for example, if we wanted to determine whether or not a number was negative or positive, we looked at the far left bit and we said if that left-hand bit is a 1, then the number's negative, and otherwise it's not negative, which means it's either 0 or positive. Okay, so if we put whatever false means, so in the case of asking is the number negative, false would be 0, 0, and true, meaning negative, would be 8, 0. Okay, because that's the bit patterns that we saw. And then, so we have to put one of them into register 0 to compare against. Okay, so what would happen is the jump would take place if the thing in register X is equal to what's in register 0. And that would jump us along um, to here, okay? And if this jump does not take place, then we'll go immediately to the do thing. Um, so let's maybe look at an example um, more specific than this. So let's do let me do a new file, and let's do let me just save this. So let's do assembly check if neg. Oops, .asm. Okay, so so let's just write basically the check if negative kind of code. So for this, we need to load numbers into registers. So let's start by loading register 1 with whatever's in E0, and let's load register 2 with whatever's in E1. Okay, so that's pretty standard like before. And then well, actually, we only need one number here because we're just going to check one number. So how did we tell? So let's make this program do the following. Okay, let's say that in Python it's if num is less than 0, output oh, I don't know, -1, else output 1. Okay, and I'm just making up that part of it. So let's say that the number starts in memory cell E0, okay, kind of like several of the programs you guys are going to write. And we want to tell whether or not this number is negative or positive. Okay, so how do we do that? Let me pull up our cheat sheet here so we've got that handy. All right, so there's our opcode table for reference. Okay. So how do we tell if a number is positive or negative? What's the approach? Okay, so we already said it had to do with the far left bit, right? So how do we extract the far left bit? Okay, so yeah, we need to load the bit pattern 80, and I'll load that into register 2. And then we need to do a logical AND with that. Okay, so we need to AND 1 and 2 and put the answer somewhere. So say, how about register 3? Okay, so now what is sitting in register 3 is either the bit pattern 0, 0, or it's the bit pattern 8, 0. All right, so we need to load one of those bit patterns Um, let's load register 0 with 0, 0. Okay. And then I'll write a second version of this where we load it with 8, 0 instead, just to kind of show you the two different ways that we could have done this. Okay, so then we'll do a jump, and we're going to compare register 3 with register 0, right? It's always compared to register 0. And then we'll jump to, if register 3 equals register 0, that means that our number is not negative. Okay, so let me call this pos for positive, and then the else will be the negative code, and then we'll halt. Okay, all right, now, so one thing I'm doing here is I'm writing this in sort of subroutine notation, um, like so, okay? So what happens if the number is positive? What do we want to do in this case? Okay, I chose arbitrarily that we would output the number 1 if the number wasn't negative. Okay, so actually maybe I should call this, instead of pos, not neg, because the opposite of being negative is not being negative, not positive, because the number could be 0, right? Okay, so what do we want to do? We want to output the number 1. Okay, so I need to load that into a register. How about register 4? And then I'm going to store it someplace. How about E2 in memory? And then we can halt. Okay? All right, does that make sense? Okay. All right, now, if the number is negative, what do we want to do instead? We want to load with the bit pattern for -1. And what is -1 in 2's complement hexadecimal? Okay, so I can't just type this. That's not permitted, right? What do I have to type instead? Well, it's permitted on some assemblers, but this isn't one of them. Yeah, what's -1 in hexadecimal? In 2's complement hexadecimal? Not quite, Patrick. That is not that's not 2's complement. It's FF, right? Because Patrick, remember, how do we negate a number? You have to flip the bits and add 1. So if I start with 1, right, which is this, and I I flip the bits, no Mia, then I would get that. And then if I add 1, I have that. And then that gets me 1111111, which is FF. Okay, so um, okay, so yeah, so FF is -1. So let me get rid of all of that, right? And then we're going to just store it out to the register, um, or sorry, the memory address, and then we can halt. No big deal. Okay, on the next episode. No, more like the last season, namely what we were doing in February. So yeah. Okay, so I've written this in sort of subroutine style notation, which is not, we're not finished, okay, but it hopefully was relatively easy to understand that these were the two procedures that we could do. the if case versus the else case, and then now we just need to kind of, if you'll pardon the pun, assemble it all together. I can also delete this halt because the negative case also has one built in. Okay, so what I need to do, and let me actually, what I'm going to do is I'm going to leave this here, and then, actually, let me save this as a second file, um, and you'll see why in a second. So what I'm going to do, oh, it would help to give it a file name. Okay, there we go. Okay, so this one is, um, oops, that's not what I wanted. I wanted this one to be, hold on, let me full screen this so I can actually see what the heck I'm doing here. Oh, I see. I never saved it as the original. Okay, there we go. This is what I wanted. So what I'm going to do is if neg, and then this one I'll, um, let's see, I want, here we go. Okay, so I've got one version, the version number 2 on the left and the other one on the right, which actually I really should do the other way, but whatever. Okay, so what I'm going to do is, um, okay, you can leave the subroutines in the assembly, okay? However, where you're going to have to do the next step is to get this into machine code. So, oops, an assembler, okay, that program would take all of this stuff and it would spit out the machine code to go with it. Um, and so for writing assembly, this subroutine style notation is fine. The problem with this is that it won't give you the machine code right away. So that's the thing that we have to fix. Okay, is to turn this basically into a form that we can then easily make machine code out of it. Okay, so what we'll have to change here is the first thing would be that the not neg code needs to go, we need to jump to it, and the negative code, so where I see neg right there, really is a placeholder for this stuff. Okay? So these three instructions, and I wish, like, if we were in the classroom where I had a chalkboard or something, what I would do is highlight these 3 lines, or like put a box around them or something. That stuff really was what neg meant, that subroutine. Okay, and then not neg, where does it start? It starts with this instruction. Okay, so I'm going to delete that. And so this is the first instruction of not neg. And that means that this jump needs to take us. So again, if we were in the classroom, I would draw like a John Madden style arrow from this line to that line. Okay, how do you identify which order it should go? Well, okay, that's the trick. That depends on which thing you put into register 0. Because if I had put 80 in there instead of 00, I would have actually had to flip the order. Okay, so either order is valid, but it depends which order you need to use will depend on which case you put into register 0, the sort of true case or the false case, right? So it's just about how you want to think about it. Okay, so the not neg stuff starts here. Okay, but I have to give the jump instruction a memory address. So not neg really is pointing to the memory address where I am going to put the instruction load 401. Now, I don't know where in memory that's going to be yet because I haven't finished the program, but we're almost done, and we know that each instruction takes 2 bytes of memory. So let's start to lay this out. We know the first instruction will go in memory cell 00, the second in 02, the third in 04, and then 06, and then 08, and then after 08 is, of course, OA, and OC, and OE. And then that means that what's next is 10. So the instruction that we want to execute, the first instruction we want to execute in the not negative case, is load 401, and that we've now figured out is going to be sitting in memory cell 10, which means that up here where I put not neg, I need to replace that with 10. Okay, the memory address where the first instruction of the that case is, that subroutine. Okay, and then just to finish it off, we'll have that and that. Okay, so for the purposes of assembly, okay, and this is a good question, Tyler, right? This is completely valid assembly, the stuff on the right. Um, and in practice, okay, so in real assembly, you could just leave it like that. And when you run an assembler program on this assembly code, it would then just sort through, oh, he's got a subroutine, and this subroutine goes here, so I need to make that jump there, and yada yada. And it would just sort all that stuff out for you. Unfortunately, such an assembler for this language doesn't exist because I haven't written it yet. And so you guys have to manually do it to take it over to here, which is just shy of machine code. Um, yes, it is very nice. So let me, in fact, give you oops, let me go to Chrome for a second and give you an example of sort of what I'm talking about. All right, so here's a good demonstration of this. Um, so here in the window is some sample assembly for its 6502 assembly. So don't worry that the mnemonics and the dollar signs and stuff, that they mean slightly different things here. But you get the idea, right? It's just that you have assembly, 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 and then if you hit the magic assemble button, then it turns it into the machine code automatically for you, and you don't have to do anything. Okay? And if there are subroutines, so if I go down a little further um, well, here's maybe a good example, right? So I have a subroutine, and then I have this line here, BNE. BNE stands for branch non-equal. It's think of it as a fancy version of our jump command. Um, the 6502 had a bunch of different jump commands, but it's basically a jump command. And so this subroutine name is decrement, and this thing here says to branch to decrement. And if I assemble that and then hex dump it, then bam, that is my machine code. Just boom, there it is. Um, yeah, wouldn't it be nice to have an assembler for this assembly language instead of you guys having to be the assembler, the human assemblers? Yeah, yeah, it would be. Well, sorry, I haven't written it yet. Um, and actually, when I do so, I'm going to write it in like a web page version like this so that I can like disable or enable the that feature, um, so that you have to do it manually before you're allowed to do it with the automatic thing. And when this gets really fancy, so let me go down here to the very bottom, which is he defines this snake game, and it's got all kinds of subroutines. Uh, and so if I assemble this and I hex dump it, then you get, well, a whole crap ton of code. So here's a snake game in eh, under 256 bytes, it looks like. Um, which is, well, actually, it's a little bit more than 256. So maybe 300 bytes or so. Um, and actually, if I run it, it's kind of cool. Oops. right? So we got our snake game, we got our little apple, and the snake gets longer, and yeah. Anyway, okay. So point being, if we had an assembler, then what we just did, which was the act of turning this into this, would be an automatic process. Um, but we don't have such a thing. Now, we've got one more step to go, actually, which is we need the actual machine code so that we could put this in the emulator and run it. And for that, we basically just have to remember that, okay, um, load 1E0? Well, it's 11E0. And what is this one? Well, it's 2280, and so on and so on. Okay, so yeah, so Tyler, does that make sense? Sort of why, even though this is completely valid assembly, we still have to do kind of uh, do more work? Okay, good. Um, Excellent. Yeah. Now, to the question about the order that Patrick asked, let me just make sure um, uh, that this is clear. That in this case, the notice that the else came first and the if part came second. That was because I put 00 um, into register 0 for doing the comparison. If I had put 80 in there instead, then these two would have been in the opposite order. Okay, so it doesn't actually matter really which order you put them in, but the order is going to be determined by what your comparison pattern is. Um, anyway, okay, so in this case, I've really written an if else then, I guess, rather than an if then else, but whatever. Um, okay, does that make sense? Save that. And the other thing I should stress, guys, is like the whole point of the fact that Joel wrote this emulator is for you guys to freaking use it, right? So last semester, every semester that I've taught this stuff, somebody turns in a project that has um, that does something like this. Let me run this little program here. Okay. If I run your code and I get it says that there's an illegal instruction, what does that tell me? Well, yes, it tells me there's broken code. Okay. But what else does it tell me? Like, under what condition would you turn in broken code? Either you're lazy, you couldn't figure out how to fix it, or what often is the case, you never bothered to actually test it to see that it was broken. So you didn't even know that you were turning in broken code. Um, and let me just say, gentlemen, nothing irritates me more than when I'm, you know, given basically a turd on a piece of paper and like you don't even recognize that it is a turd. Um, that makes me a sad panda. So please don't do that. Okay, yes. So use the freaking emulator, right? It's here for our resource. It's really great that Joel wrote this many years ago, and I have actually got a lot of features I want to add on top of it, um, like highlighting and color coding and the ability to adjust how fast it goes, and then ultimately an assembler for it. But you know, we'll put that on my bucket list. Okay, so that was good. Any what other questions do you guys have? That might be a good idea, Tyler, right? Is if you recognize that you've got a problem, just say that you recognize that you have a problem, because then I'm less of a sad panda. Um, then yeah. And guys, look, I've done that when I was a student too, right? I remember, um, for example, I was in a chemistry class, and we had to compute the number of somethings in some reaction or what, I don't remember. And I got some number that was like clearly ridiculous, like it was more than the number of atoms in the observable universe. And so I wrote a little note to the professor and I said, I'm pretty sure I've made some sort of error because this number is ridiculous, but I'm not sure what error I made. So hopefully you'll see it. And if not, maybe we can figure it out later. Um, and of course the professor circled exactly the error I had. I had forgotten to take a square root or something somewhere, and so my number was just ridiculous instead of being correct. Um, so anyway, yeah, if you know that you've got something that's not quite working, this is why putting comments in your code. Okay, so anything that you want to be sort of a textual comment, to me, to yourself, write that along with your code, and that you guys will be surprised as to how helpful it is to have um, to write comments to yourself when you're writing this stuff. Okay, to help you keep your thoughts organized. This is the other reason that this sort of subroutine kind of thing is kind of nice because it means that you can write pieces of code and then, if you'll pardon the pun, assemble them together. So, yeah. Okay, so good question. Um, yeah, so Teague's got a good observation here, gentlemen. So he says I wrote down what conditions my jumps jumped and it was a godsend. So under what condition does this jump take place? Um, like write it out in English or something, and it will really help you keep track of everything. Um, Now, for a program like this, which was not in and of itself all that challenging, right? Where this is going to get ridiculous, though, is um, when you get to the point of writing the entire program for yeah. Um, and yeah, paper, Nick, thank you for that comment too. Working this out on paper is also good because it forces you to think step by step by step. And actually, I learned a new term for this yesterday, uh, which is kind of funny. It's called rubber duck debugging, okay, or rubber chicken debugging, whatever. So for lack of a better way of explaining this, um, I'm going to use um, I'm going to use a prop here for my office. Um, this is my turret. Okay, so hopefully you guys have played the game Portal at some point in the past, or Portal 2. So this is my portal turret, and it even makes noise if I remember how to turn it on. It's got like a little electronic gadget in, in a naughty place of it. The battery might be dead. Okay, here we go. Yeah, I'm still here. Ah, maybe the battery is dead. Okay, but anyway, so I've got this cute little turret. Okay, and so it would have helped to turn it on. Yeah, I think the battery's dead. Okay, anyway, so I've got this cute little. That was a quote. Yeah, it's well. I mean, look at it. Look where it is, right? Um, so anyway, rubber duck, uh, rubber duck debugging is the following. Well, let's see, Mr. Turret. So the first step is I need to load the register with the bit pattern 80, okay? And then I need to determine whether or not that number is positive or negative. So I have to load a mask in so that I can do an AND mask. And then I do that, and then I need to jump by comparing to register. Oh, crap, that's where it should have been register 3, not 5, or whatever, right? So when you basically walk through and I know it sounds stupid, but speaking out loud, even if it's to yourself or an inanimate object like my cute little portal turret, um, then um, that will help you find and think through the process here. This would work, of course, a lot better if we were on campus because um, having the rubber duck be another live human is actually helpful because they can ask questions and you can go back and forth. Obviously, that's what happens when you and I talk about this stuff. But um, actually, I should mention because my friend Tony would love this. So I got this portal turret as a groomsman gift for a wedding I was in. Okay, and it's got a little tag on it, which is the Aperture Science logo, and it says, and you guys won't be able to read this on the camera, but it says Tony and Karen, testing complete, June 14th, 2013. So anyway, so here's to you, Tony and Karen. Okay, so we'll put this little guy down there. Yeah. So all of those, yeah, I know that was kind of cute, right? Um, all of those things are going to be good techniques to help you guys run through this, and the subroutine stuff, being very careful to keep track of what conditions you're using, and don't try and do everything at once. Document your code, work things out on paper, um, and so on. And um, yeah, because nobody sits down and writes an entire program just in one sitting, right? Especially a complicated one. Like, I don't even do that, and I've been programming, well, longer than you people have been alive. So, anyway. Okay, so good. Um, all right. Any other general questions? And if not, I wanted to kind of show you guys how addition circuitry works, or a way of making it work with Logisim, because I think it's kind of cool. Sorry, I've got some Spotify music on so that my microphone doesn't go out. All right, well, unless I see something else, I'll go over here to Logisim. So, what we were doing last time was I showed you guys how to build a single unit of memory. Okay, so this thing would hold one entire bit. Okay, and then that's it. So let me delete that. And what I'm going to show you next is how to do an addition circuit of two 1-bit things. Um, so the first thing that we're going to do is what's called a half adder. Okay, so I'm going to need to have 2 bits, and then under what condition do I have an addition? Well, I have an addition if both of them are a 1. Okay, and otherwise I don't. Right? So that hopefully makes sense. And um, so the way I'm going to think about this is my sum is going to be, so let me get up here and find my XOR gate. All right, so let me position all this stuff here. Okay, and then I'm going to wire it up. Like so. Okay, and then let me put an output here and another output here. All right, so I'm going to call this output in A1 or 0, say, and I'm going to call this input in B0, and then I'm going to call this output, this will be sum 0, and this will be carry 0. Okay? So when I do addition, um, so think about writing down 1 plus 1 like on a piece of paper, right? Uh, there 1 plus 1 is 0, but then you carry a 1, right? Or 1 plus 0 is a 1 and you don't carry anything. You have a carry of a 0. So this unit right here is what's called a half adder. It takes in 2 bits and adds them, and it produces the sum for that bit and also a carry if there should be a carry. Okay. So let's use our little finger tool here, and we can see that if I have 1 plus 0, I get 1 with no carry. If I have 0 plus 1, I get 1 with no carry. If I have zeros, then I get 0 with no carry. And if I have 1 and 1, I get a 0 with 1 as the carry. Okay, so do you guys buy that this correctly does addition for 1 bit? Oui ou non? Okay, so we Gucci with that. All right, so what I'm going to do is I'm going to make another circuit that's going to be connected to it, and I'll do that down below here. And I'm going to call this input in A1 and this one in B1. So I'm thinking of this as being the far right bit, and then I'll do the next bit over. Okay, but what's going to happen now that I'm in the not the far right bit position if I were adding up numbers? What could happen? Right? So I still have to compute the sum of the 2 bits like here, which is going to require something that looks like my half adder. But what happens to this carry? So like in this situation where my carry is a 1, the carry comes and then it will influence this sum. Yes? Does that make sense, guys? So what I need is a slightly more complicated circuit, which is called a full adder. All right, so let me draw this thing up here, and just bear with me while I make it. I'm looking at some notes so that I get it right. Okay, and then we need the AND gate here, and another AND gate there, and then finally an OR gate here, and this goes there, that goes there, this will come over here, that will go there. And this one goes here. That comes here. Okay. And then the final thing is that this carry from the previous step needs to come around, and he will connect to there and there. And then I will put some outputs here, and then I'll label them. Okay, so this is the answer in the first bit, and this is the carry of the first bit. And, okay. Yeah, so the carry of the previous bit becomes an input for the next bit. Okay, so what I have highlighted right there, this thing is called a full adder because it adds 2 bits but also takes into account an input carry from, say, a previous bit position. Whereas this chunk is only called a half adder because it doesn't take into account any carry from the previous bit position. And if there is no previous bit position, there's no need to worry about a carry from something that doesn't exist. Okay, so this is a lot more complicated, obviously, right? So let's do a situation here where we have a 1 and a 1. Okay, this would be adding 1, 1 plus 1, 1. So what would we get? We'd get 0 carry. 1, 1, 1 would make 1 carry. And so what do we have? 0, 1 with a 1 as the carry out of the final spot. Okay, so how do I turn this into an 8-bit adder? Well, I basically just need to make 7 more copies of this thing, right? Or 6 more, right? So an 8-bit adder would be 1/2 adder plus 7 full adders, all strung together. And that gets a little bit ridiculous, as you could imagine, but that's how it's done. So does that kind of make sense? Right? I could keep this game going all day, right? So I could take this and be like, okay, I'll just keep this up. So let's copy down here and let's scroll. And then this carry needs to come around and be here. Okay, and I could just keep this game up as long as I wanted. So if you wanted to do, for example, a 64-bit adder, like would be present in a modern processor, you're going to have one of these um, and 63 of those. Or actually, what you'll probably find is actually 64 of those. But um, yeah, which, each of these requires, in this particular arrangement, took 5 gates, 2 XORs, an OR, and 2 ANDs, each of which we've seen from our circuit construction used 2 transistors. So there's 10 transistors right there. Um, yeah, it is possible to do these in other ways that get the same effect, but this is maybe the easiest one to kind of understand. Um, so yeah, and we could actually build subtraction circuitry too using sort of the similar idea. We just have to kind of think through under borrowing and carrying um, for subtraction in the same way that we would have to think through addition. Um, so hopefully you guys think this is kind of cool. And can I get a shout out? Anybody who's going to keep going and be a CS major or minor? Um, no? Nobody? Crickets? Like Mr. Love, I know you're going to be a CS major. He's probably thinking, yeah, right. Um, yeah, minor. Okay. Well, so if you like this circuit stuff and you like assembly, take CS241. It'll be awesome. Um, and if you don't like circuits and you don't like assembly, don't take CS241. So anyway. Um, All right. Well, we've got just a couple minutes left, so it's the last day at the last class time of the last day in the last semester of the year, so let's wax poetic for a moment. This has been a fun semester. It was significantly more fun the front half than the back half. Thank you, coronavirus. But it's been fun being your fearless leader through bugs and code and whatnot. Um, and so the only thing left that you guys have to turn in, of course, is the assembly project due next week. So um, have fun with that. It should be exciting, maybe a little frustrating, but that's could be worse. Of course, let me know. Oh yeah, I didn't mean it like that. Once the class got a bug, we couldn't have as much fun. Yep, that's true. Once the world got a bug. Um, Sorry. Um, yeah, so if you guys have questions on the assembly stuff, hit me up on Discord. Just type a message in the text channel for CS101. And if I'm online, then I'll hop right in. And if I'm busy or not online, then I'll get to it when I am. Um, yeah, I think that's pretty much it. So thank you guys for a good semester. And I hope you all have great summers doing whatever it is you were planning to do, and that not too much gets canceled thanks to coronavirus. Um, so one thing I still need to do is give you guys a link to Logisim, and then also all of our cookbook stuff. I need to upload that to Canvas. So I'll just zip up the file and upload it to Canvas. In fact, why don't I actually take the opportunity uh, to um, show you guys how to zip something. All right, so let me delete these things where I forgot to give it a file extension. Um, and one thing I should also mention is you'll notice in here that there's a couple of file types that are of different than ASM. So we had okay, and obviously I'm not going to give you guys task 1, the code for task 1. That would be too much fun. Um, so um, let's see, what was I going to say? There's a Py file because I've got a for loop that I wrote in Python as a sample. I have my sample assembly C file, and then these S files. So the convention that I learned was if you are producing assembly by hand, you give it the file name ASM. If you have a program, a compiler produce the assembly for you from high level code, you have it give it the extension .s, and that way you know what is machine produced assembly versus what's human produced assembly, and then you don't mix the two up. Okay, so just to remind you guys on Windows how you zip things up, just select all the files that you want to zip, right click, and you're going to go send to compressed folder, and then okay, I'll just name that as cookbook. And then I'm going to fire up Canvas. So let's just go straight on over to Canvas. And let's go to CSC. And then we'll go to Files. And I'll stick it here in the assembly folder. So we're going to upload our cookbook. I want to upload it as is. And then on the main page, I'll make a cookbook link. And assembly cookbook.zip, and there you go. All right, so that stuff is all up there on Canvas, so you can just download, unzip it, and you've got all of the different examples that we've run through that aren't already included in the notes. And then actually, while we're at it, let's go to Logisim Evolution. Let me just put the link to that in. And make this a hyperlink. All right, so there we go. All right. Okay. Yeah, you can submit this in Word if you want. Um, ASM is what you would name it as if you were doing this in Atom or some other thing. However, one important point, right, is Patrick, write 4 separate Word files, one for each task. And under the project submission, I have made it so that it will only allow you to upload zip files, or if anybody happens to know what gzip, rar, tar, or tar.gzip, if you know what any of those things are, you probably wouldn't be in CS101. But anyway, so if you do write it in Word, make sure that the hyperlink is there, um, and then you're just going to zip them all up and then turn that in. So good. All right. Well, gentlemen, I'll go ahead and quit the stream. Thanks for playing. And hope you guys have enjoyed the semester. Hope you guys have learned a lot. Um, and there's still time for me to uncancel the final exam. What do you guys think about that? You want to do a final after all, just for old time's sake? That's what I thought. Yeah. I'm just playing with you guys. No, we're not having a final. Yeah. We'll report your stream. Yeah. Okay. Fair enough. Yeah. No, no, I'm not going to actually do that. I'm just joking with you guys. So, yep, the assembly project's it. So, get that done, and then you're released from your computer science slavery for now, anyway. All right. Well, I'm going to stop the stream. So have a great rest of the semester, what little remains, and a good summer. And hopefully, I will see you all in person in the fall, and everything will be back to normal.